Hi, I'm Frank Locke. I'm the Electrical Superintendent at AngloAmerican's Dawson mine. AngloAmerican's #1 priority is safety to all our people at all times. You're about to watch an animated reenactment of an incident that occurred at Dawson in July 2009. Two electricians were working at the wash plant when the arcing incident occurred and caused serious injuries or burns to their face and hands. They received immediate medical treatment and thankfully later fully recovered. We want to make sure that this does not occur across our sites or across the whole industry. This video has been put together to demonstrate why the incident occurred, the events that led up to the incident and the controls that missed along the way. At AngloAmerican, we believe that zero harm is achievable. It's up to all of us to prevent these incidents from ever happening again.
It is early morning at an open-cut coal mine in the Bowen Basin. Electricians Dave and Andrew have been asked to do scheduled maintenance on the mine's raw coal system. Part of the task requires them to inspect the high-voltage slip rings on the raw coal stacker. The stacker is fed from a 22,000-volt distribution unit that requires specific high-voltage isolation permits and detailed procedures to be followed. Dave and Andrew obtain these necessary permits and follow the correct procedures in isolating the unit. After working all day and completing their task on the stacker, Dave and Andrew are unable to close the circuit breaker at the 22 kV distribution supply point to repower the stacker. After several unsuccessful attempts, Andrew informs the night shift supervisor of the problem, and at the end of their shift, they both go home. Both are later called back to the site, but neither they nor the night shift electricians succeed in further attempts to close the circuit breaker. They both return home again. The next morning, Dave and Andrew finally discover that the circuit breaker switching mechanism itself is the cause of the problem. Inquiries reveal that there are no spare mechanisms in the store. After contemplating their options, the supervisor instructs them to remove the switching mechanism in the hope that it can be repaired. The supervisor, in the meantime, consults an electronic copy of the original equipment manufacturer's manual to see if it can offer some solutions. But unfortunately, it does not contain any reference on how to remove the switching mechanism, or any reference to the tools or materials required to do so. Attempts to find a manual on the internet and telephoning the manufacturer's agents are also unsuccessful. By the time the supervisor returns, Dave and Andrew have successfully removed the faulty mechanism. They inspect the mechanism and discover that it has a broken spring and is too badly damaged to be repaired. The supervisor instructs them to remove an identical switch mechanism from a spare unit at a nearby distribution point. However, in removing this spare mechanism, the actuating springs inside the unit lost tension, making the switch unusable as a replacement. Every effort to recompress the springs in the workshop was unsuccessful. During a meal break, the decision is made to remove another mechanism from a third unit at yet another distribution point. This time, however, they decide to lock the springs in place by drilling and tapping some holding bolts into the switch. On arrival, Dave and Andrew hold a verbal take 5 to decide the best course of action for the job. They decide not to apply for an HV access permit, as they believe the job is extra low voltage because they will not be entering a high voltage cabinet. Dave isolates the unit by turning the actuating lever that switches the mechanism to open. Now that the switch is turned to open, Dave begins to drill and tap the front fascia to secure the springs and prevent them from decompressing again. After locking the springs in place, Dave tries to remove the mechanism but is stopped from doing so by a mechanical interlock inside the high voltage cabinet. Attempts by Andrew to lever the mechanism over the interlock are unsuccessful, so they decide to remove the cover of the high voltage cabinet and get at the interlock and free the switch. Andrew returns from the workshop with a non-contact testing device to test the three-phase spouts for any high voltage in the cabinet. With the cabinet's cover now removed, he proceeds to test that the three 22 kV high voltage outgoing phase spouts are dead. The tests show that there is no high voltage present. However, approximately 20 volts is present. They detect this voltage with a handheld digital multimeter, which they use after the high voltage non-contact meter detects low voltage presence. They decide this is residual voltage that poses no threat. Thinking it is safe to proceed, they defeat the mechanical interlock and remove the switch from the control shaft that operates the isolation mechanism. They then load the switching mechanism onto the back of Mark's vehicle so he can take it back to the workshop. Dave and Andrew start to reassemble the HV cabinet just as Mark drives off. Andrew reaches inside the cabinet to replace the mechanical interlock. What has just happened? What caused the explosion? Let's step it back and try and view this in slow motion from a different angle. We can now see that Andrew's sleeve brushes up against one of the exposed high voltage spouts, creating a phase-to-phase short circuit between the 22 kV spouts. This results in a tremendously violent high voltage flash that instantly fills the air with vaporized copper, intense UV light, ionized air, and temperatures of thousands of degrees centigrade. Both Dave and Andrew are engulfed and both receive serious burns to their hands and face. But how did this happen? Dave was convinced that he de-energized the unit when he turned the crank handle to open, and Andrew had tested it for dead just minutes before. If we go back and view the high voltage unit from the inside, we can see exactly what went wrong and what contributed to this accident occurring. Looking at the animation, we can see what happens when the actuating lever is cranked to de-energize the unit. Dave only worked the actuating lever on the lower isolation crank, causing the train to lift off the live ring main unit and sit in the middle, or open position on its tracks. Once the switching mechanism was removed from the control shaft, there was nothing to hold the train in place, and gravity simply acted to pull it downwards, eventually remaking contact with the live 22 kV ring main. If Dave had also worked the actuating lever on the upper earthing crank, the train would have been moved all the way up the tracks and into the earth spools. Later testing proved that this would not have held the train in place when the switching mechanism was removed. However, it would have dissipated the residual voltages found in the spouts during the test for dead. In either case, neither Dave nor Andrew had identified the threat that removing the switching mechanism from the control shaft actually posed. They had insufficient information on how the mechanism worked and how to remove the switch safely. They believed their training and experience would see them through. Sadly, they were wrong. Hazard identification, risk management, and high-risk tasks must be controlled through the use of defined processes and documented procedures. These procedures are mandatory and cannot be changed without following the statutory processes for reviewing and amending standard operating procedures. Being unable to find the necessary information in a manual or online, or to contact the original equipment manufacturer, no one was able to adequately identify and control the hazards associated with replacing the switching mechanism. This is clearly a stage gate decision point, the first point where the job should have been stopped. Not having an authorized procedure to do an unfamiliar task on a critical and high-risk piece of equipment. The workings of the switching mechanism are a complex and unfamiliar task. This became more evident when the springs on the second mechanism fell apart on removal. This was the second decision point where the job should have been stopped. Recognizing that the task had changed and the process was not under control. To keep the springs compressed on the third mechanism, Dave used a makeshift drill, tap and screw technique to make up for his lack in knowledge of how the high voltage isolation mechanisms worked. Yet another decision point where the job should have been stopped. Surely this would not be the way an OEM would recommend it to be done. To attempt to pry the mechanism over a mechanical interlock that was designed specifically to prevent its removal is the worst type of poor practice. This should never have been attempted, and again, the decision should have been to stop the job. Finally, the decision to open the high voltage cabinet without following the correct isolation procedures and obtaining the proper permits is a clear breach of practice and can never be tolerated. The job should have been stopped until the necessary authorizations were obtained. The homegrown controls of opening the switch and testing the spouts for dead was clearly flawed and very nearly cost them their lives. It should also be noted that isolating a piece of equipment and then dismantling the isolator used as the isolating point is also a fundamental error in isolation practices. This leads us to some important lessons to share. Despite the fact that there was more than one experienced team member involved in this activity, they all failed to identify the potentially fatal hazards associated with this task. The quality of the hazard identification and risk assessments conducted by people doing a task is limited by the experience and expertise of the people present. This can provide for a fundamental weakness in the quality of the controls developed and can lead, as in this case, to people incorrectly believing that they are working safely. Always follow the OEM's instructions, the correct site procedures, and obtain the right permits and authorities. Never take shortcuts and never ever defeat an interlock. They are your last lines of defense. Dave and Andrew are incredibly lucky that they only sustained burns from this accident. The extent of these burns were lessened by the use of PPE that was worn at the time, especially the wearing of safety glasses, which prevented them both from losing their eyesight.